Okay, now that we understand what lists are and how they're represented, let's see how to calculate with lists. Okay, we're going to see in this unit a number of different ways of doing that. First of all, let me show you how to build a list piece by piece. Let me take the list here, x1, and say 5 bar x2. Now, assuming that x2 doesn't exist yet, I have to declare both x1 and x2. In the usual declare instruction, as it's written here, I will only declare one variable and have it correspond to x1. But in fact, I also want to declare x2. So what I will do is use a variation where I have an in between the declare and the in. There's two identifiers and both of them will be declared. So I do this. I have now created a data structure 5 bar followed by an unbound variable. I'll show this. You can see here 5 followed by an unbound variable written as an underscore. And now we can further bind this variable. We want to do x2 is equal to, for example, 6 bar x3. And this instruction, we only want to declare one new variable corresponding to x3. So I do x3 in, because the x2 we want to use the old one. So if we now look at the browser, notice that it has been updated automatically, saying 5 bar 6 bar unbound variable. And if we just look at x2, it'll be 6 bar unbound variable. And the final one, to finish the list, let me bind x3. Let me bind it to 7 bar nil. Here I don't need to declare any new variables, so there's no declare. So let me feed this region. And now the original x1 will be 5 bar 6 bar 7 bar nil. Now if you notice what we've done here, we actually can build a list piece by piece, and during the building it might have unbound variables in there. That's not a problem. Actually, that's a very powerful ability which we will use in a little while. So that's the first thing I wanted to show. The second thing I want to show is built-in functions. Okay, we've already seen append, but let me show you the most useful built-in functions. These are the ones using the dot operation. Now remember that a list can be seen as a tree with a left and a right subtree, where the left subtree is accessed by a 1 and the right subtree is accessed by a 2. So if I say, for example, browse x1, which is the list I just created, dot 1, I will get the left subtree, which is 5. If I say browse x1.2, I will get the right subtree, which is the list 6, 7. Notice that. If I say something like browse x1.2.1, I will get 6. You see, with sequences of dot operation, dot 1, dot 2, or dot 2, dot 2, dot 1, you can go down the tree, which is the list, and pick exactly the part that you want. Okay, that's the second thing. The third thing I want to show you is comparison. We can compare lists using the if operation and the equal operation. So for example, I can say browse if, now I'm using the if as an expression, if x1 is equal to 5, the list 5, 6, 7, then I will output 100, else I'll output 200. So this one will display 100 because x1 is indeed equal to 5, 6, 7. Okay, I can also do a comparison, a not equal comparison, which is written \equal in Oz. So I use exactly the same if statement, except that I change the condition to its opposite, so it will show 200. Okay, so those are interesting, building a list in pieces, using the dot operation comparison. Now, with this, we can do something more sophisticated. Okay, let's build a recursive function that uses a list. Okay, that works on a list of any size because it takes advantage of the recursive structure of the list, and it follows this recursive structure using recursive function calls. So here, let's make a function that makes the sum of all elements of a list of integers. So sum L, if L is equal to nil, then 0, else L dot 1 plus sum L dot 2. Okay, so this function, notice how the recursive call works. It calls the recursive itself recursively using L dot 2. So in fact, it follows the recursive structure of the list. So the recursive structure of the data corresponds exactly to the recursive structure of the function. And that's a general rule. That'll always be true when we build recursive data structures. So let's try sum of x1. This is the list 5, 6, 7. And this gives us 18. You notice here. Now, let's go one step farther. Notice that the original sum is not tail recursive. Well, we can use the same idea of invariant programming with lists as we did with integers. We can make a version, let me call it sum2, which will be tail recursive, and so the stack size will be constant. That's really important, because more important for lists than for integers, because a list can be very long. A list can have millions of elements, and if the function is not tail recursive, then the stack depth will be proportional to the length of the list, which can be millions deep. And so this is really, really unacceptable. So the use of tail recursion is especially important when you do functions on lists. So let me actually just write the result here. I have a list and an accumulator, L and A. If L is nil, then A, else sum2, L dot 2, A plus L dot 1. You see what I'm doing here? I'm going down the list from L to L dot 2, and I'm adding in L dot 1 into the accumulator. Can you write down the invariant that corresponds to this? Let me execute this. Sum2. Let me use again the list x1. The initial value of A is 0. And again, this will show me 18. Okay? So this particular version, sum2, is very efficient. It's actually exactly a loop with a stack size that's constant. Let's give now another example with another termination condition. We've traversed down the list until the end of the list. Well, let me show you a recursive function on lists that doesn't actually terminate at the end of the list, but terminates at another place. So let me define the function nth with a list n, element integer n, which returns the nth element of L, where the first element, second element, whatever element that you ask. Okay, so here's the definition. Nth Ln. If n is equal to 1, then the result is L dot 1. Otherwise, else if n is greater than 1, then nth L dot 2 n minus 1 and end. Notice there's a third condition. If n is not equal or greater than 1, then in fact there's going to be an error. But let me run this. And let me show, for example, how it works. Let me return the list x1. Let me return the second element of this list. And this returns 6. Now remember, the list is a list 5, 6, 7. Okay? Notice that this example uses recursion in an interesting way because it ends on n. It actually recurses on n and not on the list. So if the list is longer than n elements, it works fine. If the list is shorter than n elements, you have a problem. What happens if we look for the 10th element of a list that only has 5 elements?